Hi, my name is Bradie Ferguson, and I am an undergrad at the University of Washington. This summer, I've had the privilege of working in the Geiger Lab with Dr. Maryellen Geiger and Dr. Madeleine Durkee through the CDAC Summer Lab program here at the University of Chicago. Today, I'm presenting my research on radiomic texture analysis of immunofluorescence images of lupus nephritis biopsies to predict patient progression to end-stage renal disease. Lupus is an autoimmune disease in which healthy tissues are attacked by the immune system. Lupus nephritis is the manifestation of this disease characterized by the chronic inflammation of the kidneys. This can lead to end-stage renal disease in which the kidneys no longer function. The cellular mechanism that causes this progression is not well defined, making it more difficult to treat. To address this unknown, my research is focused on finding a multi-feature classifier that can distinguish between kidney biopsies that do progress to end-stage renal disease, ESRD positive, from those that do not, ESRD negative. The dataset I'm working with consists of about 1,100 images from 45 different patients. On the right, we see an example image with the 6 different cell stains. These images are ran through a radiomic texture analysis software to extract values for 20 different texture features. On the right, the visualization shows how a roaming region of interest goes through the image and extracts the values to this 2D array on top. This 2D array can be thought of as a distribution of texture feature values, and thus the mean, standard deviation, and skewness can be calculated for this texture feature. These are referred to as summary metrics in our research and helps bring the data set to a smaller size, making it more manageable to analyze. Receiver operating characteristic area under the curve analysis is performed to determine how well the different ROI size, texture feature, and stain combinations perform in the task of classifying between biopsies that do progress to end-stage renal disease from those that do not. An AUC score of 0.5 is equivalent of guessing and is thus not good. An AUC score of 1 is perfect because it identifies correctly whether or not a biopsy is ESRD positive or negative 100% of the time. These AUC scores will be used to determine which feature combinations can be used for classification. Here are some of the results. This plot is for the skewness summary metric. Stains are indicated by color, and ROI sizes are indicated by shape. If we zoom in on one of these plots, we see that this is actually an overlap of the 6 different shapes, meaning that ROI size does not impact ROC performance. There are 6 AUC scores above the 0.65 threshold, which is statistically better than the 0.5 guessing. These come from stains 1 and 2, CD20 and BDCA2, and the highlighted RTA features on the x-axis. Here's a similar plot for mean, where now 8 AUCs are above the 0.65 threshold, with the majority being from CD20 and the highlighted texture features on the x-axis. Finally, we have the standard deviation summary metric plot. Visually, we see that there are higher AUCs across the board, with now 12 being above the 0.65 threshold, all of which are from CD20 and BDCA2 stains. The texture features that contribute to this are highlighted on the x-axis as well. In conclusion, in the classification task between kidney biopsies that do progress to end-stage renal disease versus those that do not, the summary metrics of mean and standard deviation, the CD20 and BDCA2 stains, and the GLCM texture features of correlation IMC1, IMC2, and max correlation coefficient performed the best with the highest AUC scores. Region of interest size did not impact ROC performance. These results will be used in future work to train a multi-feature support vector machine and a VGG19 convolutional neural network for deep learning to increase the performance of this classification task. A huge thank you to everyone who has made this research possible this summer. Those at the CDAC Summer Lab Program, the Geiger Lab, and the Clark Lab, and a special thank you to my mentors, Dr. Maryellen Geiger and Dr. Madeleine Durkee. Thank you for listening.